All right, so it says Tara really wants to win lunch with Miss Cheryl. And so we want to do the smallest number of degrees that she can spin in order to win. And we also wanted to sketch that angle on the axes. So if we take a look here at our spinner, we know that our paperclip, we're starting here. And if we land on a line, we can choose either of the two prizes. So I had some folks say 180 degrees here, which would still get us lunch with Miss Cheryl, but 160 degrees is an even smaller angle that still is lining up with that prize. I had a few people say 151 degrees. That would certainly get lunch with Miss Cheryl, but it could be as small as 150 degrees. So that's the angle that we're going to begin by sketching here. And when you're doing a sketch of the angle, I want you to include three things. And so we're going to draw in the starting position. And then we're going to make a little sketch of a line of the ending position. So just kind of estimating here, that seemed to be about where 150 degrees was. And then the other thing that we're going to include in our sketch is an arrow like this showing us the rotation part. So what is the direction? In this case, we're going counterclockwise to get our angle measure. And we'll also go ahead and label that ending position line with the amount of degrees. In this case, we have 150 degrees. All right, so here's a little bit of vocabulary that we're going to add to this picture. So I'm going to switch to my other color. Well, that starting position that we talked about is what we're going to call the initial side of our angle measure. And then we're also going to give a name to the other line that we drew where it's ending at 150 degrees. We call that the terminal side. And the angle that we're measuring, the rotation part, is just however many degrees we have to travel to get from the initial side to the terminal side. When we have our drawing set up like this, where the initial side is placed where it is, we call this angle in standard position. So your angle might end up in a different place. Your terminal side is not always going to be at 150 degrees. But if your initial side is starting in this position here, just like the rules of our spinner game said, we say it's standard position. So taking a look now at question 2, it says that Tara actually spun 510 degrees. And we're going to see if that was still enough to win lunch with Miss Cheryl. So if we go back over here to our spinner, we can see here, well, 510 degrees, that is greater than 360. And so that would mean that she would have had to have spun more than one time around the circle. So one full time is going to get us 360. We could keep going, as we talked about a little earlier. If we continue adding 30, we're going to get some new labels here for the same position. And it turns out that 510 is going to land us at exactly the same spot as the 150 mark is. That angle just went around one full time, and then it traveled the distance that it needed to go to get back to that exact same position. So let's see what this sketch would look like. So we're still going to have our same starting position here. That's still our initial side. We actually still have the same location for the terminal side as we did before, but now what's going to look different is that arrow that we draw to show the rotation. That arrow is also going to show us not only the direction that we're rotating, but how many times we've had to rotate around. So because Tara had to go one full time around and then a little extra, it actually is going to look like kind of this spiral looking shape. So we follow the full path of that little line there. One time around is 360, and we would go a little bit further to get all the way to 510. So she really just went one more time around the center, but she was still able to land in the same place. Okay, so what we are looking at here, that measure of 510 degrees, and then over here the measure of 150 degrees that we started with from the first problem, these are two different angle names for the same terminal side position. And we actually have a special name for the relationship between these two angles. We call them coterminal angles because they share a terminal side. And it's very easy to get from one angle to its coterminal angle because it just means we're traveling one full distance around the circle and we're landing in the same place. Well, how many degrees do we go if it's one full time around a circle? How many degrees are in a circle? 360 degrees. So another way to think about this is that if we started at this measure here of 150 and we just go around one full more time, we're really just adding 360, and that's how we get the new measure of 510. So let's notice here that the original position label of 150, all we had to do is just add 360 degrees to end up in the same position. So let's go ahead and write off to the side here. So the second vocabulary piece we have here, we'll call these coterminal angles. And the way that we find it is we take our original angle measure and we simply add or subtract 360 degrees. So this can go either direction. Like imagine we started with 510 degrees. Well, if we subtract 360, we're going to end up with 150. All right, let's take a look here at part 3. So it says, well, Reed broke the rules. He broke the rules of the game, and he spun clockwise instead. So he was rotating in a different direction. He actually spins 35 degrees clockwise from the starting position. So if we were to draw that here, this is our starting position, and we're going 35 degrees clockwise. It's kind of like 35 degrees backwards of what we originally were doing. The terminal side might look something like this. So a little more than that 30-degree vector size, just a tiny bit more. It's 35 degrees backwards. But then it says that Nick actually followed the rules of the game. He landed in the exact same spot as Reed. So that means that Nick started in the same place, but he rotated around the correct way to land in the same spot. What is the smallest number of degrees that Nick could have spun? So how could we find the degree measure of the angle there in green? How did you do that one, Benjamin?
At first sight, it would be 30 degrees, but now I realize it's now 330.
Okay, yeah, very close. So if we think about starting with like 360 degrees is one full time around the circle, well, Nick almost made it one full time around, but he stopped a little bit short. How many degrees short was he? 35 degrees. So really we just need to subtract that 35 degrees, however much he fell short, and we see that he actually went forward a distance of 325 degrees. So originally that 35 degrees that we labeled, where the person went backwards, they went clockwise, they went in the other direction, we need a way to state that an angle has been drawn clockwise in the other way. And so instead of just writing this as positive 35 degrees, we would maybe get that confused with an actual positive 35-degree angle that would be somewhere up here. And so all we're going to do to this is we're going to put a negative sign in front to indicate that the direction is the opposite way. So positive angle measures go counterclockwise, like the rules of the game. Negative angle measures go the other direction. They go clockwise. So let's make a note of that here off to the side. That moving clockwise gives us negative degrees. And I'm actually going to add in my picture over here for that negative 35-degree label, put that little arrow in to show that we're going in the opposite direction. And while we're at it here, let's just say the counterclockwise direction that we started with, that's how we get positive degrees. The last interesting thing about the two angle measures here in this problem is that this positive 325 and negative 35, that's another example of two angles that are coterminal. Two different labels for the same terminal side. And if we see how they're connected, if we started with 325, we could subtract 360, and that's going to get us negative 35. From negative 35, we could add 360, and that's going to get us up to 325. That's another example there. All right, we have another interesting thing happening here in the fourth problem. So when this student went, it says that the spinner point landed 2 centimeters to the right and 3 centimeters up from the center of the spinner. Let's see if we can draw that here. So 2 centimeters to the right, just kind of estimating here, and then 3 centimeters up. I'm just going to make a point here, showing where it landed, and let's actually extend that line all the way to the center. So we can envision, that's like our paper clip, where the spinner stopped. And we don't know what angle did this student spin. And so I'm going to put in that symbol theta that we saw a little earlier in the week to represent this unknown angle that we're trying to solve for. And so the hint here was to draw a triangle on the axis. What's kind of nice about this is that where that spinner landed, that diagonal line, that would make the hypotenuse for a right triangle. In fact, we can just draw a vertical line straight down from that point, draw it straight down to what looks like the x-axis, and right here would be our 90-degree angle. So I'm going to actually transfer my label of 3 centimeters. Instead of labeling it there on the y-axis, which is not wrong, I'm going to label it over here as the height of our right triangle. So we can make a connection here to the right triangle work that we've done earlier in the week. So if we look at where our angle measure is labeled, notice how this 2 centimeter label on the bottom would be the adjacent side. And the 3 centimeter label here, that's on the opposite end of where theta is, so that would be the opposite side. And technically that diagonal line there, that's our hypotenuse, but we're not going to need to do anything with the hypotenuse at this point for this problem. We're just going to focus on the two here that we have labeled. So we're actually going to be able to set up an equation here using one of our trig functions. So we've been talking this week with right triangles about SOHCAHTOA, in this scenario, which one of these trig functions would we be able to use that would relate the information we have? We're going to do tan. Yeah, so we know the opposite side, and we know the adjacent side. So if we know that the tan of some angle theta is equal to opposite over adjacent, if we fill in the pieces that we know here, our opposite side is 3, and the adjacent side is 2. So it's kind of like the trig equations that we saw yesterday where we had a missing piece that we were solving for. But now it's not a side length that we're missing. It's actually the angle that we're missing. And so it turns out there's a little something special that you can do on your calculator that's going to help you to solve for a missing angle. And what it's called is doing the tan inverse of the answer part is going to tell us the angle here that we're looking for. So I'm going to write kind of a related equation here down below. If the tan of some angle theta is equal to 3/2, we can rearrange this and say, well, if we want to solve for that angle, we can do the tan inverse with a little -1 symbol up there. That's what that represents. The tan inverse of the answer to see what our angle should have been. And I want to show you how this looks on your calculator. So you can do this on your graphic calculator. You can do it on a scientific calculator. If you have the tan button on there, like we saw yesterday, you can do this. So right above tan, you'll notice that in a different color on my screen, it's the color matching the second key. It looks like the tan inverse function. So it's got tan, and then it's got the little -1 up here. So in order to get that, I'm going to press the second key first. Second tan, notice how it looks like the little tan inverse symbol. And then we're just going to plug in our value here. So in this case, it was equal to 3/2. You can just type it in as a fraction. And this answer here is telling us what angle is supposed to have a tan of 3/2. Now here's something kind of cool. This is how you can check it. Let's actually do the tan of this angle to check and see if it equals 3/2. Now we have the decimal digits here. If you wanted to just test it by rounding it to a few decimal places and retyping it in, you can do that. It'll be a little bit off though because of the rounding. If you want to be exact here, we can press seconds and then press the negative key at the bottom. That ANS stands for answer. It says exact previous answer, no rounding. And so when we do that, we see that our answer is 1.5, which is the value of 3/2. And so this is a way for us to think about working backwards. To go ahead and write this on our paper, though, I am going to round this maybe just to 1 decimal place and say it's about 56.3 degrees. All right, we had a lot of learning targets for today. We actually have 4 of them. I'm going to start by dividing this. First, I'm going to divide it into thirds, but this middle section here, I'm going to divide it in half. All right, so that's going to be our setup to summarize our big ideas from today. So first learning target here was to be able to draw angles in standard position with both positive and negative angle measures. So learning target number 1 is about standard position. All right, so this is going to be for an angle with a vertex at the origin and one side on the positive x-axis. So when we say origin, we're thinking about this being on top of a coordinate plane, which is a fancy way to say an x-axis and a y-axis. So this is our coordinate plane. The very center point here, that's what we call the origin. And one of the sides, the initial side, we labeled it, is the one that's right here. So it's right on top of the positive x-axis. All right, then the other side that's used in creating the angle is the terminal side. And the terminal side could be anywhere in the circle. We looked at one today where it was at the 150-degree location. So we want to draw, like, where is that angle measure ending? And then we're showing that arrow, showing the rotation that the angle is, the rotation that we've traveled to get to that angle measure. And so we saw today that if we rotate counterclockwise, it is going to be a positive angle. Just going to use a little angle symbol there. Whereas if we go clockwise, we get a negative angle. All right, so let's look at our second learning target here. This was just to find coterminal angles for a given measure. So these are angles in standard position. That share a terminal side. And it's very easy to find them. So from our given angle or from our starting angle, we either add 360s or we subtract 360s. And that represents just traveling one full time around the circle, and it's going to get us right back to where we started. All right, our third learning target here was to use an inverse trig function to find a missing angle. So let's say find missing angle using inverse. So we did one example at the bottom of the front side. Here's another example for you. So let's say that we knew for some right triangle that the sine of our angle theta was equal to like 1/3. Opposite side is 1, hypotenuse is 3. And we want to figure out what that angle is. So to get the angle, we are going to do the inverse sine of the answer part, the ratio part, in this case the inverse sine of 1/3. And we can do this one easily in our calculator as well. We'll just press second sine, and that'll get us that inverse sine function. All right, and then learning target number 4. So this is also something that we did in the last problem on the front side, is to find trig ratios for angles in standard position. All right, so for this process, we're going to use the point given and make a right triangle starting at the origin. Then we did that inverse process to help us solve for the angle. So what's a little different about the explanation here, so it's kind of like what we did in the last problem where we knew that it was 2 centimeters over and 3 centimeters up. What they might tell us in a future problem is that the terminal side of our angle passes through the point 2, 3. So when it says the point given, we're thinking about, okay, where would that point be plotted, and what quadrant would it be in? So in this case, we have positive x and positive y values in the first quadrant, so I'm putting it here. The first number in the point is going to correspond to the direction along the x-axis direction with 2. The second point listed is going to correspond to the y direction. It's possible, though, that you could be given a point that's going to land you in a different quadrant. If you want to quickly turn your paper back over to the front side and put in a couple more of these possibilities, we could have been asked about a point in the second quadrant. So the second quadrant is where x values are negative, y values are still positive. If it was something like this, we would actually label the x direction of our triangle down here, we would label it as a -2. So we want to have our labels match whatever the coordinates are. If it was down here in the third quadrant, this is where x values are negative and y values are also negative. And then over here, if we had a point in the fourth quadrant, this is where x values are positive, y values are still negative. So this just gives us a little idea of, okay, if we have the same size of triangle, if it was rotated around, we'll have slightly different labels based on if x or y is supposed to be positive or negative. Okay, so on this last circle for today, we do know what a lot of the labels are already, because they're going to match what we did in our spinner game. So at this initial starting position here, I'm going to go ahead and start with a label of 0 degrees. This first stop is the same label that we had before in our spinner, 30 degrees. Skip over a line to get to 60 degrees, and then I'm going to finish up here at the top with 90 degrees. So notice that those ones that we've labeled so far, we can see that, nope, these are equally sized sections of what we labeled. They're all jumps of 30 degrees. So can you tell me how many degrees would we label this line here that's kind of cutting through the center?
40 times.
Okay, yeah, so exactly halfway between 30 and 65, halfway between 30 and 60. So if we think that one full jump is 30 degrees, well, if we're only going halfway, it's just going to be half of 30, so we're only going up 15. So as we go around the circle, like sometimes when I'm trying to label one of these from start to finish, I just think, well, the bigger size jump that I make is always worth 30 degrees. And then here, if I'm making a smaller size jump, that's going to be worth 15 degrees. So we're either adding 15 degrees or we're adding 30 degrees. So let's see if you can continue that pattern. Go ahead and finish labeling the rest of your circle. Okay, nice job. So we just have 4 brand new ones that we added in here. All the ones that end in 5. The rest of them all ended in zeros. So these are some that you're going to see in your assignment for tonight. One more thing I want to say here, and then we're going to move into some time to get started working. So when we are thinking about, so if you look at the blue paper of your assignment, the whole first side, you are going to be drawing angles in standard position. So there's an example that's been done for us there in the first box. The size of the circle that you see with all the little lines drawn is going to look like this one, so it's going to include these highlighted options that we just added in. There are some negative angles on here. And so negative is traveling in that clockwise direction. But here is an example I want to give you. So let's say that we wanted to draw 45 degrees and then we also wanted to draw negative 45 degrees. Well, positive 45 degrees has an initial side. The initial side is always here. This would be the terminal side. See if I can draw that a little bit better. And we're going counterclockwise because we want it to be positive. If we're wanting to draw negative 45 degrees, we're going to go in the clockwise direction, but we're still only traveling 45 degrees. We're not going all the way around our circle to get to positive 45. That would be traveling way more than 45 degrees. It's actually going to end us up at 315 degrees. So when you're thinking about those negative angles, like you can definitely think about them as being coterminal. Like look at these two labels. They add up to 350 degrees. It's just this small distance that we're going backward. Sometimes a mistake that students make, if they're trying to draw to go away. If they're trying to draw negative 45 degrees, sometimes they draw the terminal side at positive 45 degrees, and they draw this huge angle going all the way back to it, but that's not negative 45 degrees. That's actually traveling like negative 315 degrees to get all the way up to that position. So those are just some pieces of advice I want to give you on the blue part. So similar to what we've had the other days in the week, we're going to, I would have you guys start with the check for understanding questions here. So that's the first part of our assignment that I'll be checking off on Friday. And then the blue paper for today, it does have a back side, front and back. We needed a little bit more room for all the angles that we're drawing. So this all together in our homework that'll be due at the start of class on Friday. So it says here that we want 6, negative 8 to be a point on the terminal side of an angle. Okay, so here's how we can think about plotting this point. So we want to think about what quadrant it's going to be in. So this is where we looked at like, okay, in this case the x value is positive, the y value is negative, and so it looks like it's going to be a point over here in what we would call the 4th quadrant. So that's our point. And then we can turn it into a right triangle by drawing a line, a diagonal line here connecting it to the origin. And then we can make a vertical line. I always make mine a little dotted, connecting that to the x-axis. And that's what's going to make this a right triangle, or a right angle. All right, so we've got the angle drawn on the axis. Now, if we were to go ahead and label our side lengths here, instead of thinking of that as an xy point, let's just go ahead and label this side length here, like on the x direction is 6, the other side length here in the y direction. I'm going to keep the negative sign attached to that, so we're going to label it as negative 8. All right, so the next part here is that we want to find the sine, cosine, and tangent ratios of our angle. And since we're not sure what our angle is yet, we can just use the theta symbol. And so we know that sine is opposite over hypotenuse. So we can see here that from where this angle is measured, negative 8 is going to be the opposite side. And our hypotenuse is this diagonal side here. Now we could do Pythagorean theorem to solve for that third side. It actually doesn't matter here if you plug in positive 8 or negative 8 for that part of it, because when you square it, they're both going to become positive. And so this ends up being 36 plus 64, which is equal to 100. And so that is really c squared. So if we square root both sides, we get that third side length is 10. So that should help us out in getting the other two written out, and you can just keep it in the form of a fraction. So save those two for you, but let's take a look here at part C. Part C wants to know how many degrees is the angle. And so this is where we can think about working backwards to solve an angle measure on the inside using side lengths that we have in the triangle on the outside. So let's take a look at maybe using just like these exact values that they gave us in the points that it was passing through, so the 6 and the -8. You could do this with really sine, cosine, or tan, depending on what two sides you want to use. But I'm going to go ahead and try this with tan. And this is actually going to connect to our answer that we got up here. So the tan we know is the opposite side over the adjacent side. And those were the two values that they gave us in the points. So to solve for our angle here, we would need to do the tan inverse of that answer. We're going to do the tan inverse of -8/6. So let's see what that would end up being. So if we do second tan, -8 divided by 6. Notice how it's giving us an angle answer that's negative. So let's think about how that negative, let's maybe just round it to -53 degrees, how that connects here with our picture. Measuring our angles in standard position is always going to start here. So if we're going in this clockwise direction, yeah, we are going to end up with a negative angle measure. So that would be one way that we could give an angle name to this terminal side position. We could also get a positive angle if we wanted to think about starting here and traveling in the positive angle, counterclockwise direction, still ending in the same spot. Well, that would just be a coterminal angle to the one that our calculator gave us. So it would really just be adding 360 to get a different label for the same position. So as a positive angle, it could be 306.9.